Welcome back to ECE 320A. This is a special session. This is a session to try to review for exam number 1. Yes? Yes, it will be recorded. I'm not being recorded right now. It's not synchronously recorded, but I will post this. And if you want to fall asleep later, you can watch it or listen. But what I want to remind you of is the exam is on Thursday. You know, okay. There is review material on D2L, and I have included a little bit more material. It covers more three-phase problems from old summer exams, summer of this year and summer of last summer. 320, but only look at the first 5 problems. The second 5 deal with future material. I hope that's clear. Don't be typing me saying, is this going to be on the exam? Problems 6 through 10 on those old or previous exam 2s will not be the material for this exam 1. But it does give you more practice with 3-phase material. That's the idea. I also have tried to make it so that you can look at some homework solutions more fully worked out than just seeing the answer or correct on mastering engineering. Those are available at the bottom of Units 1 and Unit 2. Some people said, oh, I didn't know those were there. So if you want on D2L, there are pages of worked homework solutions if you want to see how I might have attacked a problem. Tonight what I want to do is first state the exam process, then identify some key terms or phrases. When you're reading these problems, you might want to become alert to certain phrases or words that you might want to keep track of, and then we will work as many examples as we can, and that's supposed to be a question. If you have questions as we move through this session, please ask, and I will try to repeat that for those that were not able to make it tonight, and they will watch the video. I was reassured that that would happen. No. Exam number 1, process. Let me get this all on one screen. You are allowed 1 sheet of notes. That's 8.5 by 11 inches. Those quote marks stand for inches. I've had people ask what that is. It's not feet. So don't come in with a carpet full of notes, but you can have the front and back of the sheet. You can bring a graphing calculator, something to write with. If you need to sketch and you like to be very neat, you can bring a straight edge, you can bring a ruler. If you're keeping track of these vectors, you can even bring a protractor. That's fair game. Oh yes, you need to go out and buy a drafting kit. So the question was, do we really need all of that? No, if it makes you feel comfortable, you can bring it. If you use that to normally solve your problems, please bring those. But if you don't, it's not required. I'm not going to be checking as you come in the door if you have your ruler, a straight edge, and a protractor. What's not allowed is, besides your neighbor, you're not allowed a computer or a cell phone or textbook or the class notes. You do get 1 page of notes, but you can't bring in your notes. What will the exam look like? It will look like previous exams. I don't yet know, but it'll be somewhere in the range of 5 to 10 questions. They are long answer. You're not going to be bubbling in any multiple choice, not on this exam that I'm aware of. And the questions may not be equally weighted. Some might be worth more points than others? Question? I will try to indicate the weights by each problem, how much they are worth. And you can see that if you look at the practice exams, hopefully. But if I've forgotten, that's okay to ask, and I will try to keep track of some of those changes or typos during the exam as we go. The problems may not be equally difficult, so you may just breeze through one problem and go, uh-oh, what am I missing? No, it may just be that easy for you. Maybe the whole exam will be that easy for you. And drawing pictures is actually encouraged. The reason it's encouraged is that way you don't have to keep all of this in your head. Let's see, I've got a Y connection, and let's see, what was my phase voltage? Oh my, what was the source? So just draw yourself pictures so that you don't have to mentally keep that. You can use your mental facilities to be solving these problems and not keeping track of the details. That's the point of drawing pictures. What should you start to become alert on when you see, and I've tried to make these key terms or phrases in blue, in reading a problem, if you see total, that probably means three-phase. And if you see total, that means all three phases. If you see each, like each transmission line or each phase, then it's per phase that we are referring to. And we are working with balanced systems, and they are related by a factor of 3, right, in power. RMS, don't let that trip you up. Typically, when we write a sinusoidal waveform in the time domain, the coefficient is usually a peak magnitude. But a lot of the formulas that I use, I like to keep track of my variables in terms of RMS units, which for sinusoids just involves a scaling. If I ask you to compute the RMS value of some interesting waveform, it's usually not divide by the square root of 2. That's clear, right? That was one of your homework problems. You had to take the root mean square. You first square the waveform, you take the average of that, or the mean, and then you take the square root of that result. And that's now basically an effective value to replace that complicated waveform. Now you can view it like, oh, a constant waveform, and it has the same power absorbing characteristics as that weird waveform might have had. Line voltage. When you hear line voltage, again, you want to sort of wake up and pay attention. And where is that line voltage being referred to? At the terminals of the load or at the terminals of the generator? And if it's at the terminals of the generator, that usually means A and not A prime, little a and not little a prime. Those are the terminals that you would have access to. The impedance of the generator is internal to your source, and you really wouldn't have access to that terminal inside the generator. Sometimes that may actually be 0, or there may not be. It may say neglect the impedance of the generator. And the notation here, and a lot of times when I say load voltage, it will just be a number. It won't be a phasor. It will just be a magnitude. And that's what I'm meaning by capital V sub capital AB without a bar. That's just a number. Likewise, if it's at the terminals of the generator, now my subscripts are lowercase. Those are at the generator or source side. Line current, contrasting that with the phase current. But the line current is the current flowing through a transmission line, like I sub little a capital A, or capital I sub little b capital B. Phase current. If you have a Y-connected load, the phase current is the current going through that particular phase, the A phase, which in a Y connection, that's the same as your line current. But if you had a delta connected load, then the phase current is actually the current flowing through that A phase, which is between terminals A and terminal B, and that's not the same as your line current. It all depends on the interconnection structure. Likewise for the phase voltage. The phase voltage in a Y connection is from the terminal to the neutral. In the delta connection, and these notes will all be available to you, so you don't have to struggle to try to keep up with all of this, but if it helps you make the connection as to what I'm talking about, please feel free to take notes. But in the delta connection, the phase voltage is capital V sub AB. I said that because I'm trying to get through this somewhat quickly so we can spend most of our time working problems. If I say something like a reference phasor, what does that mean? That's where you get your stick and draw a line in the sand, isn't it? That's where you are labeling or referencing time t equals 0. And that now has an angle or a phase of 0 degrees. If I say, oh, assume the A phase transmission line is your reference phasor, now you know that capital I sub little a capital A has an angle of 0 degrees. Or I might say, assume that your phase voltage at the load is 0, is your reference phasor. Now it depends on what your interconnection structure is, which of those ANs or ABs you would assign to have 0 degrees. Ooh, I was doing this too late, wasn't I? No, when phasor quantities are numerical values and what? No, when phasor quantities and numerical values are used in formulas. Here's what I'm trying to mean by that. In the first example, those are actually phasor quantities. Complex power is VI star. In the second example, the total power in a three-phase system, we derive that, and that's in terms of your line voltage magnitude, your line current magnitude, and the cosine of the angle of your impedance, or your power factor. And those are expressed in RMS magnitudes, where the line current is always the magnitude of VAB, no matter how your load is connected. That's your line voltage. Transmission line to transmission line voltage. That's what V sub L is. And that maybe is what you measure. Your line current is the transmission line current, the current going through your transmission line. That's I sub little a capital A's magnitude. And that maybe is knowable. Now you just have to know the power factor, and you can compute based on a magnitude of the line voltage, a magnitude of the line current, and the power factor. You can determine the total real power. You can do the sine of that angle to obtain the total reactive power. Then you have the total complex power by vectorially adding those components. Questions on key words. What did I forget? I could have forgotten something, but I want you to start to become alert when those words are used, so that you can put them in the right location or use them properly. Questions on that? All right, let's get serious here. Bless you. I've prepared a little bit here in advance. Here is, let's say, problem 1. Ooh, that's pretty left justified, but I don't think I can scroll over to the left. Oh well. I can scroll down. Now, if you're reading this, how would you maybe read this? And there I've indicated that it's worth 18 points. But the first thing that I would start to be paying attention to is it says, oh, a single phase equivalent. It's probably a 3-phase problem, and I need to extract a single phase equivalent from that 3-phase balanced system. And the system must be expressed in terms of voltage sources and impedance. And if you wanted to, you could just quickly start saying, oh, I need something like this. Meaning there is my source with the internal impedance. I have a transmission line impedance, and I have the load impedance, which Z sub capital A, since it's balanced, all of these I could pretty much forget the little a's on those. It's balanced. But this is what I'm trying to produce with this single phase equivalent. And now I have a picture of what I'm trying to work on. The generator has a positive phase sequence. So I might just there say, okay, I have an ABC phase sequence. And it's providing a total real power to the rest of the system of 900 watts. So now you know your P total is 900 watts. That doesn't mean that you can assume that Q total is 0. It's just that I've only told you the real part, or the average part. And that's of the generator. So you could say either generator or source, for example. Assume there is no internal impedance in the generator. So now you know that that's 0, which means that it's not open, but it's a short, right? So if I was giving credit for nothing, then you would get some points for 0. I don't know. If you had this picture drawn and you'd put a 0 there, I might say, man, that looks like something I'd do. They need some points. Out of 18, maybe you'd get, I don't know, half a point. It's better than nothing. All right. Now what do we know? The real power absorbed in each transmission line equals 20 watts. What's the key word there? Each. So now I'm switching things a little bit. Now that's each. Now I know right here, this is 20 watts plus J something. Let's say Q sub L. So I haven't yet read that. But I know that's 20 watts in that particular impedance in the transmission line. The line voltage magnitude at the load terminals is whatever, 156.8 volts. Where's that? The line voltage. It's not even on this diagram, is it? That's from A to B. Trick, 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 trick. What's the key word? It's not tricks, but you just have to pay attention, right? Line voltage. Question?
We weren't given, it says that the real power is
Yes, so if this is a balanced system, the question was if the statement that I just finished, the real power absorbed in the transmission lines equals 60 watts, then you could divide that by 3 and get the per phase power in the transmission lines. Because all three, they're balanced, they have exactly the same wattage absorbed or lost in all three phases. But now I'm giving you the line voltage magnitude at the load terminals, so that's V sub AB, and we're only giving a magnitude that is 156.8 volts RMS. And one of the questions that you asked was, when do we use this square root of 3 and 30 degrees? Well, this is a place where you might use that to convert between line voltage and phase voltage if you wanted to. There's many ways to solve this problem. The total are we alert? The total real power absorbed by the three-phase load is 840 watts, and the total reactive power of the inductive load is 180 bars. That's at the load. Meaning now we know that over here, P total load is now whatever it was, 840 plus J 180. How come I said plus? It was inductive. And here's where I've seen some students, it's not that they really made a mistake, they just got to going too fast. They might, if they haven't labeled that, they might think, oh, there's my impedance. No, that was a load, or that was a power, wasn't it? So this is volt amperes. That's not ohms. But they see a complex number and they go, oh, that's an impedance. No, that's the complex power. And this is the total of the load. So if we wanted it per phase, we could divide that by 3. Question? Thank you. It's late. I just did that to see if you guys were paying attention. The comment or the correction was, shouldn't that be S? Yes, well, I got put to sleep by looking at that P right above. But that was just a P, wasn't it? That was the total source power, or it was the real power of the source, 900 watts. Thank you. So this, now you're up to 1.5 points out of 18. I joke, but this will start to get you on the way to solving this problem. Now what do we do? What can we do? What in the world? How did this not copy? Oh, this is an old exam. I think, my notes are different than this. There's a power factor in this. Where did that go to? I must have somehow erased it when I copied it over. There's supposed to be a power factor of the generator, isn't there? I have no idea. Do you see it in this text? Am I that asleep? So here, there should be in here power factor of the generator, and it says it's 0.949 lagging. Now we have a little bit more to work with. Now do you see that you could create the power triangle at the generator? You have enough information. You have 2 of the 4 variables that you might want or need. We also know a lot about the complex power at the far side or at the load side. What do we need? We need to find a V sub AN, a magnitude, and then we could just assume that that's the reference phasor and give it a 0 angle. We need to somehow extract impedances from the transmission line, and we need to extract impedances from the load. We need capital Z sub A, we need capital Z sub L, and we need a V bar sub AN to obtain our single phase equivalent. Yes. Oh, yes. Yes, so the question is, what do I want based on this problem statement? And what I want is the voltage source. There's only one, so the plural you can cross out. But now you need all the impedances in this single phase. You don't have to draw the entire, and I don't even tell you how the original system is interconnected, do I? I don't tell you how the source is connected. I don't tell you how the load is connected. You don't need to know that. You can still extract the information that you need to fill in this single phase equivalent. And one of the nice things about this is then you could start finding or computing capital I sub A little a capital A. If you have all the impedances and you have the generator voltage, now it's, I think, trivial to compute the line current if you needed it. Or can we get that from some of this other information? What do you see how you would start attacking this problem? What's one unknown that you will need? Capital Z sub A, the impedance, and how do you find impedance when you have complex powers? I squared R is a place to start, isn't it? If you have this, let's say a per phase complex power, this is V phase, I phase star, which if we replaced V phase with Z, and in this case it could be Z sub A, and now if we knew the magnitude of our current, our phase current in this configuration, that would be the transmission line current. Can we somehow find the line current? If we could find that, then we could actually obtain Z sub A. Do we have enough information to try to find the line current? I'm trying to give you a hint. What was the question? Do we have S and V? Good question. Do we have S? Yeah. We do have S. That's right here, isn't it? Do we have V? Indirectly, we could have the phase voltage, but we have the line voltage. Hint. So can we use this equation? What do we have in this equation? We have P total of the load, don't we? We have the line voltage at the terminals of the load. That's what we need. We have the line current. No, we don't have the line current. Do we have the power factor of the load? Not directly, but indirectly we do, don't we? Because we have the complex power. So we can find the angle from this triangle, and that we could take the cosine of that angle to find the power factor of our load. What I just said is from this information, we can say, okay, power total of the load is square root of 3 V load, I load, cosine theta phi. Somebody said, can you go through a Sudoku problem? Which they were meaning, and that's where this is maybe different from 220. Now you're not going in a straight line from beginning to end to find a solution. You're sort of given some things all over the problem, and now you have to work your way frontwards and backwards and sideways to try to find the answer. This is the power factor of the load, and we had that the load was, where are my numbers? 840 and 180. So that now theta phi sub L is the inverse tangent of 180 over 840, which is now 12.095 degrees. And that now allows me to find the power factor of the load is the cosine of theta sub V sub L, or the cosine of 12.095 degrees is 0.9778. Lagging, if we need it. In this formula, we don't need to know if it's leading or lagging, do we? Boy, I better quit putting my head down. Who was first? Okay, question. So the question was, how much of my work do I need to show? Enough so that I know that you're not getting it from your neighbor. So what you can do is you can say from calculator. You can write, for example, you could write this down, this complex power, and say from calculator, and write that in apparent power at an angle, for example. And then you can say, oh, now I know my power factor is the cosine of that angle. So just tell me in notes. You don't have to necessarily write it all down, but I really think I hope you have enough time, and it probably helps you in the process to write things down. I think that's where we start to maybe fool ourselves as we go, oh, I can just keep it all in my head. Well, don't worry about it. Just write it down, and then if it's wrong, scratch it out. Don't spend time erasing. Then if it happens to be correct, you haven't erased the correct work. Yes? This was the total. I subscripted it T, but they are all proportional, so that angle's not going to change if I find that angle for the sum, or if I divided that by 3 and then took the angle or found the angle. So you can do it either way. If you say, you know what, I feel more comfortable looking at this on a per phase basis, but this formula is actually wanting the total power. So it's expecting the total power, which is 840. I have the load voltage, or I'm sorry, I have the voltage, the line voltage at the load, and I want to find my line current so that I can find this impedance of my load, and that will maybe help me find the impedance, at least of the real part of my transmission line. Other questions? And once I have the transmission line current, and I know the power of my generator, and I know my power factor of the generator, I can now find my line voltage at the terminals of my generator, which now I can reduce by a square root of 3, and I have my phase voltage at the generator. Yes? So the initial problem, it does not matter how things are interconnected. Is that what you were asking? So all I'm giving you in this problem statement is powers, complex powers and relationships, and I'm not telling you how things are maybe physically connected, but you can still create a single phase equivalent from that information. Do we continue, or do I just assume we have this one? Continue. Okay. That's what you want to do on the test, is continue. Don't stop halfway through. But at least you're starting to outline some information. What I'm wanting to do now is use this with this formula, so that now I know that I have 840 is equal to the square root of 3. V sub L, wasn't that 156.8? I sub L, that's my transmission line current, and the cosine of the load, I can solve that now for the line current, and did I do that? This now becomes 3.1632 amps, and everything was in RMS, so that's in RMS, and that's just the magnitude of my line current. This now allows me to find my impedance of the load, but now it is critical that you only use the complex power of one phase. Is that clear? Because this, oh, the door was locked, wasn't it? Sorry. I got you in until 6:30. And then she said she was going to come back around and lock the main door. Thank you for, boy, cell phones are nice, aren't they? And I didn't tell, well, yeah, on the exam you won't be able to do that, but hopefully the doors won't be locked during the middle of the day. Is it clear that now you can only use a third of that total power, complex power, to compute Z, your impedance of the load? This is a per phase power, so that now you would use this formula. You would say, okay, Z sub phi, which is 840 plus J 180 over 3. That's now equal to Z sub phi, or Z sub A, times I sub L squared. And we just found I sub L. That's now square is going to be a little bit more than 9. We divide this complex number by 9. and we have our impedance at the load. And now you have about a third of the problem solved. Meaning now now we have Z sub A is equal to 840 plus J180, all divided by 3.1632 squared. And if you run out of time, then you could say something like R sub A plus J X sub A. That's pretty good. If you know that, then you didn't have to spend time computing that, but then you would have to label R sub A and X sub A in your single phase equivalent. But from this, I understand that you know what's going on. That is now that piece of the puzzle. And those numbers are right there if you compute them. Questions? Now what? I thought you were going to say, can we leave? I was going to say, the doors are not locked from the inside, I hope. Sorry, go ahead. I think the question was, can we leave our impedance in polar format? I think I would like it in rectangular. Yes, put it in rectangular, because that's what I'm looking for, the resistor and the reactance. Other questions? Yes.
We're doing the single phase. Instead of leaving the box with the next to it, you want to split up its resistor and capacitor inductor.
Yes, if you have the time. I mean, if you don't, and you've already drawn this, and you now label Z sub A right here, and say R sub A plus J X sub A, you're telling me that you know this is a complex number, and I now have R sub A and X sub A if I just identify or did the crunching. Now what do? We need to find the transmission line impedance, and we need to find the voltage of our generator. Pardon? Yes, so now we know that we have this, power of the generator, and we have the angle of the generator, complex triangle angle, so that we can then find the entire complex power and divide it by 3 over here on the generator side. Let's see, we could do it many different ways. So the power of the generator total was 800. The power factor of the generator was 0.949, which tells us then that the angle of our generator is the inverse cosine of that power factor. Pardon? Thank you. I told you it's getting late. It's past my bedtime. 900 watts. Thank you. And the angle, if you do the inverse tangent, is 18.378 degrees. We can now compute, if it's however you want to do it, but you could say P sub GT is S, the apparent power of the generator, times the cosine of the theta of the generator, so that now we can find the magnitude of the generator total. And that now allows us to find QT of the generator. And if you do that, you end up with this being roughly 300 VARs. Yes? So the sign convention here, what you have to keep track of is that the source is going to supply all of the power that your load is demanding. And so in this case, if you were having to, find the amount supplied and the amount absorbed, then this would be the amount supplied, but really that's equal to the amount absorbed. And now you're setting those equal to find the amount absorbed by the transmission line. Yes. Yes, so now when we say that, well, how do I want to say this? The power supplied by the generator is going to be absorbed by all of your loads. So now essentially you know that supplied equals absorbed. And you're trying to find how much was actually absorbed. Part of it was given to you with the load, and what's left is now going to be what is from the transmission line. So now in this case, you had 840 watts here. You had how much in your transmission line? 60 total, so that gives you 900, and that's consistent between the generated and what you're using. Now we need to find the Q of the source, which is 300. Compare that to what's absorbed by the load, which is 180, and now we have the net that the transmission line is needing or absorbing, little q sub L. Meaning, q sub L now is just one phase, so let me say that the power of the generator plus JQ of the generator per phase is now 300 plus J 100. Is that okay? And that's equal to 840 over 3 plus J 180 over 3 plus 60, I'm sorry, I'm doing it per phase, 20 plus JQL. And the only thing that's left, this is 60, so that 100 is equal to 60 plus Q sub L. Q sub L is now 40. And that's the magnetizing VARs that are absorbed in the transmission line. So that now we know in the transmission line, we have S of the line per phase is now 20 plus J 40 volt amperes. And we know that that's Z sub L times I sub line quantity squared by VI star. And now we can solve for little z sub L. That's S sub L per phase divided by I sub L squared. And I think that's roughly, or is 10 in the denominator. So this becomes 2 plus J 4 ohms per phase. And that's now going to be what I can do right here. This is now 2 and this is J4. The remaining piece of this problem is then to find the magnitude of the phase voltage at the generator. V sub A n bar. And now we could use this formula at the generator side. We know the total power supplied by the generator, that was 900. We know the line current. We know the power factor of the generator. This will give us our line voltage at the generator terminals. That will be V sub AB. We need V sub AN, but we can find that by this square root of 3 adjustment, converting phase voltage to line voltage. Seeing a lot of this was given to us as 0.949. This we computed to be 3.1632. This was 900. The only remaining unknown is the line voltage at the terminals of the generator. And I ended up with V sub, whoops, as 900 divided by square root of 3, 3.1632, 0.949. That ends up being 173.1 volts RMS, but that's the line to line voltage. And we know this was positive phase sequence. That says then that the V line is equal to the square root of 3 if we were doing phasors at plus 30 degrees V sub let's say AN. But we can choose whatever we want for a phasor voltage. We could forget the angles and say that the magnitude of VAN is now V line's magnitude over the square root of 3. Question? Good question. How come you're using so darn many formulas with different numbers? Was that the question? So now here we have, so that's I think where you can get confused, is here this L, capital L on the power, is at the load. This, in this formula, is then the line voltage at the load. The line current is the same in the source and the load, but this voltage here is the line voltage at the source. Same formula applied in two different locations. And now we can complete our single phase equivalent. This is now 100 at 0 degrees, and we're done. You may want to go a little faster on Thursday. You may not get an hour for one problem. Questions on that? But I wanted to spend the time on that going slow so that you could start to see how you might use these formulas at the correct time or in the appropriate location. So now if you, so the question was, if I used maybe my voltage at the load terminals as my reference, I think is what you were saying, could I then come back and compute an actual angle at my generator terminals other than 0? Yes. That really doesn't impact this particular. I don't think it matters. The question is, which would you prefer? I think this would be the quicker way to do it than to try to keep track of the angles as you're going through the problem. But really, on these problems, you need to work them the way that you see it and not the way you think I'm going to want you to solve it. So any angle really that you have on capital V sub AN phasor is going to be acceptable in this problem. So however you ended up with it, if you said, oh, well, I had an angle back there, but I know that it doesn't matter, let me just put a 0. You could just write that. You can say, I'm going to assume after I've worked this that my generator voltage is the reference phasor. That's okay. Other questions? Do we want to do another 3-phase, or do you want to do something else? Pardon? The hardest problem. You know, once somebody asked me about power factor correction. Here's a power factor correction. This is problem 4 on the same exam. Here, it says a single phase system. So you can throw out all of those square root of 3 power formulas. Now you're just dealing with VI cosine theta as your per phase. It's just a single phase power. In a single phase system, find the reactive power, not the capacitor, but just the reactive power that the capacitor is providing, that a capacitor needs to supply to the following system. The goal is to achieve a power factor of 0.9 lagging, not a power factor of 1. That's how this differs from maybe your homework problem. Now you don't have to drive that reactive part or component all the way to 0. You just have to make it such that you have a power factor of 0.9 lagging. So you're going to have a positive Q. The original load absorbs 40 watts of real power, and so let me say power of the load is now 40 plus J 30. S. That's of the load. And we know that, well, we're given all sorts of information, and some of this information may not even be needed. But what we have, picture-wise, is we have Z load, and we are trying to now find what Q sub C needs to be to give us the answer that we're looking for. What are we looking for here? We can draw the original triangle. It's 40, 30, and so this is 50. That's a 3, 4, 5 triangle. But we want to find what's the angle that we want the entire combination of these to be. The total load, so S load total is going to be S load plus JQ sub C. That capacitor is not going to give us any real power. We're assuming it's ideal. What's the angle we want to end up with? Isn't that what we want? We want a power factor of 0.9, and that corresponds to a certain angle, cosine of an angle, to give us 0.9. If we inverse cosine 0.9, that's the angle that we are going to want after we combine all of our loads. This ends up being 25.84 degrees. And this is much bigger than 24, isn't it? We actually want that. This is what the original load produced. This is where we want to end up. This is actually Q sub C that we want to have drive us down. Can we find this Q desired? We know 40, we know theta sub D, that's just a trig problem. The desired reactive power is going to be positive, and that's 40 times the tangent of that angle we just said we desired, which was 25.84 degrees. So that this ends up being 19.37 VARs. The QD is Q, let's say, of the load plus Q sub C. Q of the load was 30. Whoops. And our capacitor needs to then give us or supply 10.63 VARs. Yes. Well, not usually. You usually want to think of a capacitor giving you negative VARs, and so I'm not sure what you're seeing there, but you might be, oh, what does the capacitor need to supply in order for this to be true? But in this case, we're not even asking for you to find the capacitor value. We're just asking you to find how much reactive power is the capacitor supplying to this other parallel load to get the entire combination to have an angle of 25 degrees or a power factor of 0.9 lagging. If you needed, how could I have made this problem trivial? I could have maybe said the goal is to achieve a power factor of 1. Then what would your answer be for Q sub C? Minus 30. Right? Because you're just trying to get rid of that reactive component of your power in the load. Questions on this? These should be somewhat similar to what you'll see on the exam, but we've only looked at 2. You might have 10. So I would recommend that you look at the practice problems or practice exams. Here's another one. In a single-phase system, find the magnitude of the voltage at the generator. So this one's playing with terminology and where things are located. You're asked to find the magnitude of the voltage at the generator terminals if the load absorbs 100 watts of real power and 40 VARs of reactive power. Transmission line impedance is 10 plus J10, and the voltage at the load terminals is 100 volts. Can you sketch a picture? You're given the load is 100 plus J40. There's your generator. You're trying to find the magnitude of that voltage here. What else are you told? The voltage at the load terminals. You're now told, and this is a single phase system, so you're now told that this is 100 volts RMS. Now what do we do? Pardon? S equal VI star, or VI conjugate, and that will give you your current, won't it? Once you have your current, you can use that current to find this voltage drop, and this drop plus this drop gives you V sub G. And you're done. I mean, it takes a fair amount of calculation, but that's the strategy for this problem. Questions on that? We're dropping like flies. Yes. So now, where do we use the reference? Now you're just told that the load terminal voltage is 100 magnitude, and you're just asked to find the magnitude of your generator voltage. So you really don't have to worry. You do need to keep track of the phasors in the sense that you have to, once you've assigned, I would probably just assign this voltage at the terminal of at the load to be my reference. Then I can simply divide that complex power by 100. That gives me my I star. Then I can use that I star as a phasor with 10 plus J10, add that to my 100 at 0 degrees, and that will give me my V sub G complex number, and I'll just have to find the magnitude of that complex number. But your KVLs now will involve complex math. And these are all worked or have solutions, but I would recommend that you look at some of these without first looking at the solutions and try to solve them, and then go and look at my solutions if you get stumped. Question? Yes, I'm going to try to extract what I've done tonight into some notes and then post that with the video. I don't know what we're doing tomorrow. So that was, the question was, what are we doing tomorrow in class? Does that mean what we do in class determines whether you are there or not? I don't know. Maybe I'll start giving you some of the answers to the exam. Not. But we'll see. I haven't decided. It may be somewhat more discussion of three-phase and single-phase equivalents. I don't know what we'll do tomorrow in class. Do you have any more burning questions? Yes. This one? Is this the first problem? Yes. It depends on how you're finding. So the question was, can I work this problem another way? And I think I do in the solutions. But if you now are looking at, you can use the total power in that phase, or I'm sorry, the complex power in that phase. You can, is that how you want to define then I sub AA? It depends on what you're doing, but if you keep track of what's the phase quantities, meaning the phase voltage would be V sub AN and the line voltage, then that VI times cosine theta would be your power in that particular generator phase. And it could be, you could, this again, this gets back to that question, where do I put my angle on the generator? You just have to keep track of it as you're working through the problem, but at the end you could arbitrarily say it really doesn't matter in this single phase equivalent. All I need to know is a particular angle at this generator, and that could be 0. Because in this problem, all I'm asking for really is this phasor voltage and the impedances, and it really doesn't matter because I could draw 0 here or I could draw 0 somewhere else relative to this sinusoidal steady state. What's important is you know the magnitude of this generator voltage and the impedances. That's really what's critical. But I want you to show me that, oh, that's actually a phasor, and if you put 10 degrees, it really wouldn't be wrong. Then that's the reference for everything else. So once you pick a reference, you have to live with it until you've finished the problem. Other questions? Going. Yes.
If you're not given mention that it's inductive load, can we just assume it's inductive load? That's why the power factor is lagging.
So now the question was, it depends on where the lagging is, meaning if, for example, you had a transmission line that was capacitive, and it was such that it ended up changing the characteristics, then you would need to know whether it was leading or lagging or inductive or capacitive. Your particular sign on your reactive power.